It's 1975 in the summer of June. You respond to a crime scene call late at night to a radiator shop in Phoenix, Arizona. Upon entry, you observe the decedent, a police officer with a single bullet wound through the upper torso. Behind him is Drywall with no obvious penetrating bullet holes, except for one odd, deep indented mark with an irregular pattern. This sparks confusion because the indentation is an uncommon characteristic for the bullet path from the entry and exit wounds on the officer. The bullet recovered is a .38 Special lead round nose, which should easily penetrate through drywall, given its properties. When investigators attempted to reconstruct the scene, they were baffled in estimating the shooter's position. So, what happened? What does the evidence show? To answer this, we need to become familiar with how projectiles in motion work on a physics level regarding penetration potential, intermediate target wound ballistics, and how gypsum drywall reacts as a material. To start, the bullet recovered was a .38 Special LRN, which appeared to be fired from a Smith & Wesson Model 15 revolver. This caliber is 158 grains, with a standard velocity of 755 to 800 feet per second, and is typically used for range shooting. In terminal ballistics, which is the study of what a projectile does to a target, there are two important subdivisions to be aware of for this case: penetration potential and wound ballistics. Penetration potential is the capability of a projectile to penetrate various materials, such as drywall, wood, and metal. For example, a 158 grain .38 Special plain lead bullet generally will fail to penetrate the outside skin of a car, while a .30-06 full-jacketed rifle bullet at a velocity of 2,700 feet per second from 200 yards can penetrate through 4 inches of concrete. There are 3 main factors that can affect penetration potential of a bullet: bullet yaw, which is deviation of bullet axis from line of flight; nutation, which is the motion in the rotation axis of a spinning body; and precession, which is the rotational effect about the mid-axis. For our case, we are only concerned with bullet yaw, which more specifically is the angle between the longitudinal axis of a projectile and its line of flight before the bullet achieves full gyroscopic stability. Think of a bullet leaving the muzzle like a football being thrown. Generally, the way a projectile should behave is like throwing a perfect spiral that has both directionality and gyroscopic stability for longer, accurate throws. Now throw the same football but with a weak hand, and it might be tumbling mid-air, losing velocity but going in the same direction. This is analogous to bullet yaw, where the bullet is traveling in the same direction but not in the same orientation. This is an important distinction because as a bullet has a greater angle of yaw, it can create misleading damage patterns at a scene. Wound ballistics is a bit more complex for this video's purpose, but ultimately a bullet can and will exhibit gyroscopic instability to some degree when hitting a biological target. Let's look at the victim in our example. The officer was shot in front through the upper torso and exited posteriorly. When the bullet immediately leaves the muzzle, it is in a slight unstable condition in between the distance of the shooter and the officer. Upon entering the torso, kinetic energy is rapidly diffused, creating both temporary and permanent cavities. During this process, the bullet is losing velocity and gyroscopic stability, while increasing angle of yaw. As the bullet exits the officer, the bullet has lost much of its stability and exhibits significant tumbling motion before it strikes the drywall behind him, creating the irregular bullet hole shape. The final factor to consider in this case is the drywall itself. Drywall does not require much velocity from a normal handgun bullet to perforate its material, generally only about 100 to 170 feet per second, but it depends on the bullet's weight and orientation. According to the 2010 research paper that this case is focused on, scientists attempted to reconstruct the shooting by testing a range of bullets and recorded their velocities when striking drywall substrates with the Doppler radar. One significant observation from the results showed that velocity loss is independent of impact velocity once the impact velocity surpasses the threshold velocity of 100 feet per second or more. Meaning that if 2 bullets, let's say A and B, where A had a velocity of 300 feet per second and B had 900 feet per second, were fired into half-inch drywall, since they both exceed the 100 to 170 feet per second threshold, they would both perforate the drywall and show the exact same velocity loss at about 50 feet per second. This is relevant to the case because the .38 Special LRN failed to perforate, meaning that its velocity had to have been below the 100 to 170 feet per second threshold. This excludes the possibility or any testimony presented that there was 1. A direct shot at the drywall, and 2. Any minor deflection or ricochet. Instead, it strongly supports that an intermediate target was the most likely cause for the .38 Special LRM bullet to cause this indentation, resulting from significant deceleration and yaw. This case is just one example showing how difficult firearms-related crime scene reconstruction can be when interpreting bullet hole evidence. If you enjoyed the video and like to see more forensic-related content, consider giving the video a thumbs up and subscribing to the channel.